Welcome everyone to For the Love of Physics. We're really glad you could join us for this deep dive. A big hello especially to all of you from Ishik Boys High School, and a special shout out to Mr. Jager's class. Think of us as maybe your extra assistant on this physics journey. Today we're going to dive into some really core ideas you're probably talking about in class right now. It's all about the fascinating connections between heat, work, and internal energy.
Yeah, and these aren't just, abstract terms from a book. This stuff is happening all around you every single day. Like, why does your bike pump get warm when you use it? Or how does a hot air balloon even lift off? It's all physics in action.
Exactly. And that's what we want to do today. Our goal is to sort of unpack these concepts, make them super clear, relatable, so they really, stick with you, ready to explore.
Let's do it.
Okay, well, let's kick things off with a big one. Internal energy. Now, this might sound a bit abstract, but stick with me. It's basically all the energy stored inside a substance. Think of all the tiny particles, atoms, molecules constantly moving, vibrating, interacting. It's their kinetic energy from moving around, plus the potential energy from how they're arranged and the forces between them. It's the substance's own energy stash. Let's make it concrete. Imagine you're pulling a nail out of a piece of wood. You've probably done that, right?
Oh, definitely felt that resistance.
Right. That resistance, the friction between the nail and the wood, well, you're doing work against that friction. And that work you do, it doesn't just vanish. It actually gets converted. It increases the internal energy of both the nail and the wood around the hole.
Okay, so, wait. When the nail feels warm right after you pull it out, is that literally its internal energy having gone up because of the work I did pulling it?
Precisely. Yes. That warmth is a direct sign that its internal energy increased. And a higher internal energy usually means a higher temperature. Then, because the nail's hotter than the air, energy naturally starts transferring as heat away from the nail. It flows to the cooler air until everything evens out temperature-wise. It's a great little example of work increasing internal energy, which then leads to heat transfer.
Got it. Work in, internal energy up, heat out.
You got it. And this brings us to a really key point, one that honestly trips a lot of people up. Objects don't have heat, and they don't have work stored inside them. What they do have is internal energy.
Right.
Heat and work, those are the processes. They're the ways energy gets transferred from one thing to another or from one form to another. They're like energy in transit, energy on the move. That movement changes the internal energy of the things involved.
Okay. That makes sense. It's like, you don't have a payment sitting in your wallet, right? You have money. The payment is the act of transferring the money. So heat and work are the transfers, and internal energy is the account balance.
That's a fantastic analogy. Yes, exactly like that. Internal energy is the balance. Heat and work are the transactions changing it. Now, when we study these energy transfers, these transactions, we need to be clear about what we're focusing on. Physicists call the specific thing we're studying maybe the gas in a piston or water in a beaker, the system.
Okay, the system is our main focus.
And everything else outside that system, anything that could possibly interact with it, that's called the environment.
The surroundings. Makes sense.
Let's use another visual. Think about a flask of water, maybe with a balloon stretched tightly over the opening. And let's say we heat that flask with a flame. The flame is part of the environment. The water inside is our system.
Right.
Energy transfers as heat from the flame through the glass into the water. What does this do? It increases the internal energy of the water. The water molecules start moving faster.
Gets hotter.
Exactly. Then, if you heat it enough, it boils. Turns into steam. Now, the steam takes up way more space, right? So it expands. And as it expands, it pushes that balloon outwards. It's pushing against the air outside. That's the steam doing work on the environment, specifically on the atmosphere and the balloon.
So the energy that came in as heat built up the internal energy, and then some of that internal energy was used up to do the work of expanding the balloon.
You nailed it. As the steam does that work, pushing the balloon out, its own internal energy actually decreases a bit. It shows the whole cycle. Heat comes in, boosts internal energy, and then that internal energy can be converted to do work going out. And of course, we should probably mention that the hot flask itself is also losing some energy as heat to the air around it. That's another interaction with the environment.
Okay, complex interactions, but the core idea is energy moving around.
Precisely. Now let's focus specifically on the work part when gases are involved. In thermodynamics, there's a pretty neat formula for the work done by a gas when it expands, or the work done on a gas when it's compressed. It's calculated as work, W equals the pressure, P, multiplied by the change in volume, delta V. So W equals P delta V.
W equals P. Got it. So P is pressure.
Yeah, pressure basically how much force the gas exerts over an area. Think of the push inside a tire. And delta V, yay V, that's just the change in the gas's volume. Did it get bigger or smaller?
Okay. Pressure times volume change.
But here's the really crucial bit about this formula.
Yeah.
Work is only done if that volume actually changes. If delta V is 0, no work is done. Think about pushing really hard against a solid brick wall. You're exerting a force, maybe feeling pressure on your hands, but the wall isn't moving.
Right. No displacement.
Exactly. No displacement, no volume change for the wall systems, no work done on the wall.
Hmm.
Same idea for a gas. If its volume stays constant, W is 0, even if the pressure goes way up.
Huh. So if I have gas trapped in a super strong sealed metal tank and I heat it up, the pressure inside could get really high.
Hmm.
But since the tank doesn't expand, the gas isn't actually doing any work, even though it's pushing really hard.
It's exactly right. No volume change, no work done by the gas. Delta V has to be non-zero. And the sign matters too. If a gas expands like our steam pushing the balloon out, its volume increases. Delta V is positive. In that case, the work done, W, is positive, and we say the gas does positive work on its surroundings, pushing outwards.
Okay, expansion is positive work by the gas.
But if the gas is compressed, think about pushing down the handle of a bike pump, its volume decreases. Delta V is negative. This means the work done by the gas is negative. Or, another way to look at it, positive work is being done on the gas by something else, like the pump handle.
Right, work being done on the system. Okay, that makes sense.
Now, real-life situations like car engines or weather systems involve really complex thermodynamic processes. So, to understand the basics, physicists often use simplified models. We call these ideal processes. They help us isolate certain effects. We'll look at two really common ones.
Okay, simplified cases.
First, let's talk about an isovolumetric process. That sounds fancy, but iso means constant, and volumetric relates to volume. So isovolumetric just means constant volume.
Ah, like the rigid tank example.
Exactly. If the volume doesn't change, then delta V is 0. And if delta V is 0, what did we just say about work?
WP times 0. So, 0 work done.
Bingo. In an isovolumetric process, no work is done by or on the system. A classic lab example is something called a bomb calorimeter. It's basically a very strong sealed steel container, the bomb, where you might set off a chemical reaction. Because the container is so rigid, the volume inside absolutely cannot change, so any energy released by the reaction can only escape as heat, usually transferred to surrounding water so you can measure it. No energy goes into doing work.
So it's designed specifically so that any energy change must be heat transfer because work is physically impossible.
You got it. All the energy change shows up as heat.
Yeah.
Okay, second ideal process, the isothermal process. Again, iso means constant. Thermal relates to temperature. So an isothermal process is one where the temperature of the system stays constant the whole time.
Constant temperature, okay.
Now, this one has a really interesting consequence. If the temperature stays constant, especially for an ideal gas, it means the system's internal energy also stays constant.
Wait, how can that be? If work is done or heat is transferred, shouldn't the internal energy change?
That's the clever part of an isothermal process. Energy can be transferred, but it happens in such a way that the internal energy stays level. Think about this. Imagine you have a balloon, maybe partly inflated, just sitting there. And let's say the atmospheric pressure outside starts to drop very, very slowly, like maybe before a storm comes in.
Okay, slow pressure drop outside.
As the outside pressure decreases, the slightly higher pressure inside the balloon will cause it to expand slowly. So the gas inside the balloon is expanding, meaning it's doing work on the air outside, right?
Right, delta V is positive, so positive work is being done by the gas.
Yes. And normally when a gas expands and does work, it uses up some of its internal energy, which would make it cool down. But because this expansion is happening incredibly slowly, there's plenty of time for heat to flow. As the gas starts to cool ever so slightly from expanding, energy immediately flows into the balloon as heat from the slightly warmer surrounding air.
So the work done expanding out is perfectly balanced by heat flowing in.
Exactly. The energy leaving as work is immediately replaced by energy entering as heat. The net result, the temperature inside the balloon stays constant, and therefore its internal energy stays constant, even though both work and heat transfer were involved.
Wow, okay, that is subtle. But it only works if it's slow, right, to allow that heat transfer to keep up.
That's the absolute key. It has to be slow, or quasi-static, as physicists sometimes say. It allows the system to constantly readjust and stay in thermal equilibrium with its surroundings. Tiny expansion, tiny cooling, tiny heat inflow, back to the original temperature, repeat. If it happened fast, like a balloon popping, the gas would cool down significantly because there wouldn't be time for the heat to flow in.
Okay, that makes a lot more sense now. The slow speed is critical for isothermal.
Right. So let's quickly recap what we've covered in this deep dive. We started with internal energy, that's the energy stored inside a substance due to its particles. Then we clarified that heat and work aren't stored energy, they are processes of energy transfer.
Energy in transit, like payments, not account balances.
Perfect. We looked at how work done by gases relates to pressure and volume change, using W-Reese events. And the big rule, work only happens if the volume changes. And finally, we dipped into two ideal processes, isovolumetric, meaning constant volume and therefore zero work.
All energy change is heat.
And isothermal, meaning constant temperature, where the internal energy stays constant because any work done is exactly matched by heat transfer.
Right, workout equals heat in, or vice versa.
So here's a little something for you to think about connecting this back to that bike pump.
When you pump up a tire, you push down on the handle. You're doing work on the air inside the pump cylinder, compressing it. Where do you usually feel the pump getting warm? Often near the bottom, where the air is being compressed. How does that warmth relate to the work you're doing and the change in the air's internal energy? And what about the opposite? If you let air out of a tire quickly, sometimes the valve feels cold. Why might that be?
Good questions to mull over. Keep exploring these ideas. Stay in contact with your physics teacher. Stay creative.